We've been wanting to try out the nitration of phenol for a long time, so here goes. We won't be making picric acid as it's very dangerous and ultimately not very useful. Instead we're going to see if we can mononitrate phenol. Interestingly, we couldn't find the definitive right cut of a procedure, so we've come up with our own from looking at the procedures that we could find. We're using the large 1-liter flask for the reaction, equipped with a thermometer and a stir bar. It seems as though it's important to keep the temperature down in order to avoid denitration, so we're going to use an ice bath. And we've got the thermometer in the flask so we can record the temperature of the reaction mixture carefully. Here's 42 mL of 68% concentrated nitric acid, which will be our nitrating agent. We notice that some procedures use a large molar excess of nitric acid compared to phenol, but they don't explain why. We're going to use about a 1.5 ratio and see how this goes. We place the nitric acid into the flask. And now here's 80 mL of water. Phenol is much more reactive than say toluene to electrophilic nitration, and so only dilute nitric acid is needed in order for the reaction to occur. This also goes into the flask. Okay, we've got our nitric acid stirring away in the flask in the water bath now. We've placed an addition funnel on top of the flask so we can add the phenol slowly. This is important because the reaction could be quite exothermic. And here's our phenol. We're using 40 grams. This is a crystalline solid, but becomes slushy in contact with water and if heated above room temperature. The easiest way to turn this into a liquid that we can add to the nitric acid mixture is to add a small amount of water. Here's 12 mL of warm water. This should be enough to form a single phenol and water layer, but not enough for separate layers to form. Let's add this. On stirring we end up with a clear mixture of phenol and water, which is a liquid as you can see here. Check that the tap is closed, and we'll now pour this into the addition funnel. Okay, we're pretty much ready. We've got a little bit of ice in the water bath to regulate the temperature, and we're going to allow this to drop a bit and equalize at around 15 degrees C before we start addition. Okay, we're there now. Let's start the acid addition very slowly. Quite quickly there's a yellow or faint orange color appearing. And this soon grows more intense and then red, and then begins to become quite dark. We're monitoring the temperature in the flask closely, and if it looks as though it's going to go above 30 degrees C, then we slow down the addition. We notice that above about 25 degrees C some brown fumes of nitrogen dioxide are also generated, so we try to keep the addition slow. Water bath temperature is about 16 degrees now. The addition took about 25 minutes to complete. The maximum temperature we hit was about 31 degrees C. Okay, all done. We allowed the mixture to stir for 15 minutes more and then let it warm up to room temperature. It's pretty dark and nasty looking as you can see. It smells very strongly of substituted phenols. Don't spill this mixture or you will never get the smell out. We've got the separating funnel set up. Now let's get our reaction mixture in. Initially there's no obvious layer, but on allowing to settle for a while, and putting the light in the right place, you can see that there is a bottom darker layer. This dark layer contains our products, the mixture of ortho and pyronitrate phenol. So we separate this layer into a flask. As you can see, it's quite viscous, and it gives off some brown nitrogen dioxide fumes. We next measured out 100 ml of water, and added this to the flask along with the dark organic layer. What we're now going to do is steam distill the mixture. It turns out that the orthonitrophenol is easily steam distilled, whereas the raw product is not, and is left behind in the boiling flask. So we've got a simple distillation setup here without a thermometer. On heating, you can see that the water starting to condense on the sides of the boiling flask contains tiny yellow droplets. This is the orthonitrophenol being steam distilled. And here it is collecting in the receiving flask, the mixture of water and the yellow orthonitrophenol. We kept distilling for 2 hours, and topped up the water in the boiling flask as needed. After this time, no more yellow droplets were coming over. Here's the residue left in the boiling flask. We'll come back to this later. First we'll deal with our steam distillate. You can see there's a bottom orange layer. This is stable for a while, but on standing at room temperature, or when disturbed, it quickly crystallizes into a solid mass. We broke this up and then filtered it. We washed with cold water and then dried thoroughly on the pump. Here's our first product. 13 grams of orthonitrophenol. This is a 22% yield on the starting phenol. Not a great yield, but it looks nice and pure, and we're happy with this. It's got a strong unpleasant phenolic and aseptic smell. Here's the contents of the boiling flask after steam distilling. In theory, this should contain our pyronitrophenol product. We've just got to find a way to get it out. There's a top aqueous layer, so first of all we decanted this off, leaving a sticky dark mass at the bottom. Here at Island pretty nasty. It stinks of phenol, is insoluble in hot water, and sticks to anything it touches, making it difficult to wash off. We chilled this in the freezer and it solidified into a dark mass, the top of which is seen to have a yellow crystalline coating. But on warming, even below room temperature, it melts again, forming the black sticky tar. We wondered if maybe this could be due to there being some unreacted phenol present. So we placed 150 ml of water and another 100 grams of ice cubes into a beaker, and stirred our black mixture into this, the idea being that the excess water would dissolve any phenol present. We stirred this mixture really well, and the black product remained as a solid in the bottom of the cold water. We use a pre-chilled glass center funnel to filter the mixture. Then we washed with ice-cold water and dried as well as we could without allowing the solid to warm up. Here's what we ended up with: a black solid mass. But again, On allowing to warm, this simply melted into the tar-like substance we had before. Pyronitrophenol has a fairly high melting point, so this is extremely impure. At this point we gave up trying to get a usable product out of this, just because it was such a mess to work with and every operation required large quantities of acetone just to clean the glassware afterwards. So if anyone knows definitively how to do this reaction and purify the products, then please let us know. But we do have our nice orthonitrophenol, and will be using in the future in a follow-up reaction. So stay tuned for more videos.